Yeah, I was working those 3 jobs, doing what I could. Let me see. Anybody else come in? No. 2, 4, 6, 10. Okay. All right. All right, guys. Any questions from homework stuff? Yes.
For number 77, what is this? 8.3.
77. 90% confidence interval. Okay. So what was the issue? Is that the one? The voting and the...
It's just the error bound. I'm not sure.
Oh, that's just the error. The plus or minus that piece.
Oh, okay.
Yeah, so when we've done this stuff here, I've told you to, this is exactly what I was talking about. Calculate this first. That's the error bound.
Oh, okay.
Yeah.
And then when it says about the distribution, what is that like? Is that the
Which distribution should you use?
Yeah.
Yeah, so this one's interesting. That really is a question like, check to see if it's normal, right? And in this case, when you have percentages, what do you check to see if it's normal enough? Is it n greater than 30? That's for means. What about for percentages? So not n greater than 30 in this case. What takes the place of that?
P greater than 5?
No? I'm sorry, what'd you say?
P?
No.
No.
P can't be greater than 1 because it's a percentage, right? It's a probability. So NP and NQ, at least 5. Yeah. So if you check those, then you can say we'll use a normal distribution. That's why you can get the z-score from the z-score chart. Yeah.
Okay. Yeah.
I like it. I like it. All right. Yes.
117 on 8.3.
All right, let's see. Okay. Insurance companies want to know the percentage of drivers who always buckle up before riding in a car. Let's see. Sorry. I'm having flashbacks to when I was younger. When designing a study to determine this population, what is the minimum number? Oh, okay, beautiful. So let me say this question. This is number 117 in section 8.3. When designing a study to determine this population proportion, what is the minimum number you would need to survey to be 95% confident that the population proportion is estimated to within 0.03? Whoa. What formula would you use? What is the let's see, the minimum number, the number? What variable is that? The number of people in your sample. What variable is that? N. So doesn't it make sense that you would want to use a formula that solved for N? And in this case, this is a percentage, right? Yes. So you want to use the N that's got the percentages in them, the z squared, p hat, q hat, over e squared. So what would the E be?
0.03.
Yes. And then how would you get Z? The fact that they want to be 95% confident, then you can look up the z-score.
So that's 1.96.
Yes. Beautiful. So you know 1.96, you know 0.03. Now p hat, q hat, did they tell us? No. We don't know shit about p hat and q hat in this problem. And by the way, again, this is number 117A. We don't have a clue what these are. So what do we have to guess they are? 50-50. 0.5. And then part B probably says, no. Part B is not what I thought it would be. That was very important. That was going to be more than blah, blah, blah. Okay, so part B is just a conceptual question. Yeah. All right, so that was number 117. Anything else? By the way, just to point this out, we do have a quiz tomorrow. Chapter 8. When's our next test? On the Monday, right? Next Monday, the 17th. When's the final exam? A week from this Thursday. Sean. Morning. All right. Just to remind you, not to again, this is summer. It's like, we feel like I just said hello to you for the first time and it's almost over. Okay. All right. Anything else from homework stuff? All right. So just to remind you guys, if you're working on like chapter 6 or chapter 7, well, those are kind of important, but it's a little more important to do more recent stuff, especially with this coming. If you don't do any of your chapter 8 homework and then you take this quiz, you're not going to do well. You need practice before you do this. Okay. All right, so get in there. Do the old stuff later when you have time. All right. Okay. Anything else before we jump back in to where we left off? Okay. All right. You guys all doing okay, relatively? Okay. All right. All right. So, I'm doing okay too. So what did we do yesterday? Holy crap. So where did we leave off? We started getting into hypothesis testing. And this is what people normally think of when you say statistics. Very often, one of the things that some people think of is those commercials that say 3 out of 4 dentists say this, or where they say it's been clinically proven that, yes? It's not been proven. Nothing like that's ever proven. They've shown enough evidence. So clinically proven just means they found enough evidence. So we're in this chapter, we're going to figure out, how the hell do I show evidence for something? If we create a new drug and we think that the drug takes less time to take a headache away from people that are taking statistics, specifically, right? It's a hyper-specific headache caused by statistics. Our new drug takes less time to remove it. How do I test that? In fact, how would you test that? You guys know this. If you create a new drug, let's say that we somehow know how to create drugs, right? I'm not talking like a Walter White situation. I'm talking, we're making in an official capacity, legal stuff. How would we test our new pain reliever? What would we do? You guys know how this works.
Studies.
Huh?
Clinical studies.
Be more specific.
Human trials.
Okay, good. More specific.
Placebo. Not
Sure, yes. Okay, you would have one group that would get our drug, right? You'd have another group that could get a placebo, right?
Double blind.
Sure, okay, so this is coming back from section 1.4.11. Double blind is the preference. Double blind just means the people don't know what they're getting and we don't know what they're getting. Now that sounds weird. Somewhere there is a connection so that later we can see, but we don't want any bias to creep in. So if they don't know what they're getting and we don't know what they're getting, there's no bias. Okay, maybe. So that's from section 1.4, which feels like a million years ago and yesterday at the same time. Okay. So what we're about to get into is, what does the statistics look like that I would actually use to analyze that situation? We know we have a group that gets a drug and we have a group that doesn't and blah, blah, blah. But what the hell do you actually do mathematically to then be able to go on TV and say, it's been clinically proven, right?
To somehow, I guess, scale the amount of pain relief they get.
So let me ask you this. Let's say that I'm just going to make some shit up. All right? Something I don't like to do, but it's just for conceptual purposes. Let's say that it takes Tylenol, it takes 20 minutes for it to get rid of your headache. You guys come with me? We create this new drug, and we're like, our claim is it's better. So what would that mean in mathish specifically? So the Tylenol, the old drug, takes 20 minutes. If ours is better, our average should be less than 20. Okay, good. So that would be the claim we were talking about yesterday, right? Okay, I like it. So then you would give the drug to a group, and you wouldn't give the drug to the other group. Now, what would show evidence? There's just, you don't know specifically, but you know kind of like what would show evidence? What would you have to actually see? If I saw in the group that I gave our drug to, if it took 19 minutes on average? How do you feel about it? Would that be good enough evidence?
No.
19 is less than 20, correct? I mean, you're all like, that much I know, man. Right? But is that good enough evidence? Why is that not probably good enough evidence?
5% is still pretty significant percentage.
Okay, be less less tactical. 19 is less than 20. Why is it probably not good enough evidence that the drug actually takes less time for everybody who takes it?
Too close to 20.
Sure, yes.
A minute.
So the distance isn't big enough, and also the fact that it came from a sample, right? So I could have just happened to pick people that would respond well to the drug. Do some people respond better to Tylenol than others? Do some people not respond to Tylenol at all?
Yes.
My poor little brother, they have to like give him triple the dose of any pain reliever. That's just the way he is, right?
Don't gingers also have like a really easy, like they can easily overdose on like painkillers or
I
something?
don't know. But if you have a study, I'd love to see it. Okay, now. Is everybody with me? So a sample actually, like if we think it's less than 20, and a sample that's less than 20, that's not good enough. It's supposed to be less than 20 enough. It's got to be far enough down from 20. Does that make sense just by itself? You knew intuitively that 19 probably isn't good enough. If we had a sample and we gave it to them and the average was 14 minutes. How do you feel about that?
Pretty good.
Better, right? What's missing? What's the information we don't know right now that's missing that's really important to determine how far something is from something else in statistics?
Yeah.
Yes, standard deviation, kick ass, right? So real quick. If the mean is 20 and the standard deviation is 5, is 19 very far from 20? Is it even one full step down from 20? No, it's 1/5 of a step down, right? You guys with me? So what if the mean is 20 and the standard deviation is 0.01? Is 19 very far from 20?
Yes.
It's 10 steps below 20. Holy shit, right? Okay, good. So this is what I meant earlier this semester when we first learned about standard deviation. The huge thing in statistics is distance. If I want to show something is less, not only does it have to be less, it has to be far enough less to be evidence that everybody would react that way. Maybe. So not far, crazy far, right? Okay, I was gonna say hella far. Thankfully, I didn't say that. Now, let's see. All right, I'm trying to tease out which way I want to go because I got crazy amounts of handouts today. The main one is this one. So let's review what we did yesterday. I told you there's 5 total steps. So far, we've talked about 2 of them, right? So let's do this. You can do it, John. No, let's not do that. Let's just review this. So we have a claim that's made. So in this case, the claim, like you said, was the mean was less than 20. We thought that our new drug, would take less than 20 minutes to alleviate somebody's headache. So that's the claim in Mafish. Didn't like it. Anybody remember where that goes? If you weren't here yesterday, you're like, what the hell is he writing up there? What is that?
That'd be under the alternate hypothesis.
Alternate. What's always true about the statement you put next to the null?
It's got an equal sign somewhere.
It's got to have some kind of equal sign. So the null is always going to have this symbol, or this symbol, or this symbol. It's got to have an equal sign. It's the part that thinks it's in the middle. The ha will always be the one I can show evidence for. I can show evidence that it's more than, less than, that it's different. Yeah.
But the alternate or original null hypothesis, neither are dependent on whether or not it's what you're trying to prove your claim, I guess.
The claim could go either place.
Okay.
Yeah. Is that cool?
Yeah.
Okay. And we'll see that. Shit, did I make? I think I did. See if Past Jeff made a good problem.
Oh, so I guess the alternate and original, they're both hypotheses.
No, I made horrible problems. Okay.
They're both hypotheses, so that either way can be a claim. It just depends on
Yes.
of like
Yes.
what you're trying to claim.
So if the claim, all right, real quick, where does that claim go again?
Alternate.
Alternate. And so what would the null or the ho?
Greater than or equal to 20.
Yeah, the opposite of this. Okay, let me stop for a minute. So again, I always think of this as two old men in Starbucks. One guy's like, you should read this, is crazy. The other guy's like, what are you talking about? It's perfectly fine. Right?
I think I kind of understand it. So it's or I understand like why you put it there, but is it because like the null hypothesis is everything but what you're trying to claim, like trying to prove everything except this as a way to like disprove it?
The way we've decided to set this up, and there are a lot of different ways we could have set this up, but this is just the way it was sort of standardized, is the ha will always be the thing I could show evidence for, and the ho will be things I could show evidence against.
Okay.
If I take a sample, if our sample of our people that take our drug, if the mean comes out to be 20 minutes, does that mean that the mean actually is 20 minutes for everybody? No. The sample just was 20 minutes. The actual mean could be anything. I cannot show evidence that something equals something. I can show evidence that it's not equal to that thing.
Okay.
Maybe. So in this case, will this be a one-tail test or a two-tail test?
What?
Yeah, because what's the only, where do we want our sample to show up? To show evidence for this guy.
To the left.
So here's 20. We think it's less than 20, so there's only one side that would show evidence. So that would be a one-tail test. So eventually, that one-tail thing on the t-score chart will become important for this kind of problem. So now it makes more sense why that t-score chart is a one-tail and a two-tail. This is a one-tail test. In fact, don't worry. I want to do another one like this real quick. Let's say that the claim of something is the mean is 25. Let's say somebody claims the average age of gross one is 25. Can't like it. If they take a sample and the average age of the sample is 25, does that prove their claim? No. Shit, no. Samples could be anything. I don't know. Get away from me. If they took a sample and the average came out to be 38, even without the standard deviation, that feels like it's going to disprove their claim or be evidence against their claim. I like it. I love you guys. Some of you guys are like, where the hell is this pain reliever, Jeff? I already need it. I'm sorry. Okay. Somebody help me out. I want to do more problems like this real quick because I love it when I forget to do something specific. Where will that go? Which one? The null or the alternate? Which one will that go next to?
No.
Why the null? It has a equal sign. That's it. Right. What will the hobby? What's the opposite of equal?
Not equal.
Not equal. How many tail tests will this be? How can you show something's not equal to something else? It could be greater or less, so it's going to be a two-tail test. Either side will be evidence for me. This one, only one side is evidence. If I got up here, I'm completely screwed. It's the opposite. If we give her a drug and it takes 30 minutes, I'm like, oh shit, I think we've messed up here. Or the headache gets worse. And I'm like, oh, well, okay. Okay, maybe. Okay. So this would be a two-tail. All right, what about this? What if we claim that the mean is at most, let me see how it's, mean at most 38. What would that look like mathematically? At most, what is that?
Less than or equal to.
Less than or equal to. At most means that or less. All right, somebody else tell me, where would that go? Which one? HO or HM? HO, because it's got a freaking equal sign in it. That's it. That's just the way we decided. We always want the ha to be the guy that's extreme, that we can actually show evidence for. It was just a choice we made. We didn't make it, but we have to live with it because it's a choice that was made for us. So this will go here. What's going to go here?
Greater than.
Greater, just the opposite of this. How many tail tests will that be?
One.
One tail. I'm only interested in above. Below would screw me over. I wanted to show up there. I'm only interested in one tail. Okay. So let me do this. Let me see. Yeah, this one. Okay. Just to give us a little more structure, I'm going to give us this worksheet. Bless you. You're just gonna have to deal with it. All right. Let me catch up. Hold on. I've got all 5 steps down there. So every semester I'm like, how do I want to teach it? So I think this time I'm going to try to do it this way. It might make more sense with all the steps down there. We'll see. Wake up. Oh yeah. This one. Everywhere. Okay. All right. So, read through that situation if you haven't already. So on the surface of this, it should sort of make sense. If some animal is given more room to roam, then their general life should be better. That should equate to a longer lifespan. It doesn't mean every single coyote is going to live longer. It just means on average, there should be a positive effect, right? Okay. So everybody read through it. What is the claim in English?
That if they have more room to roam, then they're going to live longer than 10.15 years.
Good. So they'll live longer than would normally be expected. So what's normally expected is what you will never ever see here is anything from the sample. How would this work in real life? Before we take a sample, aren't we going to have a claim? We're going to go, I think this, and then we go take a sample, correct? So you're never going to see a number from the sample here. Because by the time we're making our claim, we don't have a sample yet. So this is we're getting everything at once. Bam! But we just got to realize, we didn't know shit about anything. We just had a claim. So can somebody else tell me in in Mathish, what the claim is?
U is equal to 10.15 years.
No. Greater than. Right? Lives longer. Look at Jeff being nice and bolding the important things. Don't get used to that. So, very often when you're trying to figure out what the claim is, you're looking for language like decreased, gotten bigger, at least, at most. If you don't see those, it's almost definitely two-tailed. So if I said the mean was 7 and I think it's the same now, okay, mean equals 7. The claim is it's the same, right? But if I see directional language, what the shit is directional language? That greater than, less than, increased, decreased, went up, went down, blah, blah, more, less, blah, blah, blah. Okay, right? That means it's going to be a one-tailed test. So this is definitely lives longer. So we think that the mean for a certain group of coyotes, specifically the ones that got more room to roam, is greater than 10.15. This is why I'm kicking myself, because the first 3 examples I've given on these various things, they're all, the claim goes in the, and real quick also, I always forget this. I think the book says ha instead of high. Sometimes some books have the hos and the highs. Our book has the hos and the ha's. If I remember correctly. Hopefully that's right. So where does that go? Next to the null or next to the alternate? Alternate, because it doesn't have an equal sign. Okay. So what goes next to the null? Less than or equal to. It's crazy. It's got to be the opposite. I love it. Is this going to be a one-tail or a two-tail test? One tail. In fact, more specifically, which tail?
Less than, or I'm sorry, greater than.
So which tail?
Right.
Right side. Okay. So it'll be one tail test. So that first step really should be relatively simple. It's just translating from from English to math, put it in the right place, and then you could just tell, is it going to be one tail or two tail? If this is not equal to, two tail. If this is less than, greater than, one tail. Yes?
I was just about to ask, so if I'm understanding this correctly, so if it either is greater than or less than, it'd be one tail, if it just has the equal sign, the slash is gonna be two tail. Okay.
Yeah, the not equal sign for the ha, yeah.
God, I wish I should figure that out years ago.
Oh, okay. Glad I could be of service. Okay, now, step B is nothing new at all. Can we use z-scores, t-scores, or nothing? And notice what I've done here is, in black is some interesting points, and in red, let me think, what was it, Jeff? Oh, in red is kind of the conceptual part, and in black is sort of the nuts and bolts part. So here, this is just nuts and bolts. Can we use z-scores, t-scores, or nothing? What am I looking for? 2 things. What tells me I can do anything?
Is it normally distributed?
Is it normal? And how do we know? Does it say it's normal?
No.
Damn it! But what saves us?
Population standard.
N is, no, that has nothing to do with it.
Greater than 30.
Yeah, N is 41, which is greater than 30. Right? So that's the good old chicken, lettuce, tomato, or central limit theorem. So that tells me I can do something. So I can cross out nothing. What tells me if it's Z or T? What do I look for? Which standard deviation do we know? And of course, which standard deviation do we know? Population, exactly. So sigma known, what does that mean we can use? Z-scores. Come on. Okay. All right, let me stop for a minute. So I would never give like a fully fleshed out problem like this on a test where the answer was you could do nothing. That would be so evil. Because again, you might go, well, I should do it, and then you waste time doing the whole problem, and so I'm never going to do that. I could have a problem where I just say, don't do this, but tell me, blah, 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 right? Yes?
But could you ever use the t-scores? Because for the claim you were talking about population.
So what would have been different here for me to use a t-score? Sample standard deviation. If the standard deviation I knew came from a sample, then I have to use t-scores because that's why they were invented.
But then you said the claim comes before the sample. So, like, it's possible to get a sample still from, like, this type of problems? Is the question.
I think, all right, let me make sure I really understand your question. All right, let me say this and then you tell me if I'm wrong with what your question is. Anytime I take a sample, can I calculate a sample standard deviation? Yeah, of course I can. in this case, we know the population standard deviation. So of course I'm not going to use my sample standard deviation. The sample standard deviation, its job is to estimate what the actual standard deviation is. I don't know if this is related to your question.
Okay, let me rephrase it. Like,
Yes.
because before you kind of confused me when you said that you need a kind before your sample, so it's like, you kind of phrase it in a way where it's like always population. So I just wanted to know that.
Oh, no. So, okay. All right. When I'm stating our claim, it would have been made before we took a sample. So the 12.45 number would never show up here because we wouldn't even have known it at that time. And even before I took a sample, don't I know the population standard deviation? Yeah. Okay. Yes.
Okay, so I'm having a hard time trying to read number one, but you wrote right there. It says 41 less than, like,
41 plus 10.
I think for part B, 1B.
Oh, yeah?
yeah.
It's-
N equals 41, which is greater than 30. Right? Yeah, okay.
I was so confused because like I think 30 or something S.
Okay. All right. Is everybody with me so far? I know I write horribly, so I have to listen as I'm writing. But please, dear God, don't just sit there and go, I guess this is my life. I have no idea what he wrote. Just ask me. It's fine. Okay. So part B of any hypothesis test will be really straightforward. It's stuff we know for sure. Part A is a little new, but it shouldn't be that horrible. Part C is also something we know. What the hell does alpha mean? We know this.
It's like one tail.
What's the area in the tail or tails? So where is the tail? We already know where it is. There's one tail in this problem. Where is it? It's up here. What's the area in this here? Yeah. So that is 0.01. Now you could look up 0.99 on the z-score chart, but we're better than that. I'm going to use the t-score chart to look up my z-score, yeah? If I have one, yes. If anybody needs one, let me know. So we have one tail. Alpha is 0.01. Right? One tail, 0.01. I mean, this chart is just made for hypothesis tests. Why did we always look here for confidence intervals? Because confidence intervals always make chop two tails, right? But now a hypothesis test could be one or two tails. So 0.01. Do I stop somewhere? I want a z-score, so I want to go all the way. 2.326. Now let me make sure. Okay. All right. This is crucial. Okay. Yes, I know hypothesis tests. They have 5 steps. I know. The way a hypothesis test works. So far we got what the hell are we talking about? What can we use to talk about it? How far away is far away enough is what we're doing right now. When does evidence start? So let me ask you this. If the middle really is 10.15, what is the probability that a sample would show up here? 0.01, 1% chance. Let me say this again. This is huge. This is everything right now, right? If the middle really is 10.15, the probability we get a sample here is 1%. So if we get a sample here, is it more likely the mean is wrong, it really is bigger, or is it more likely that it's fine and we just happen to do something that a 1% chance of happening?
More likely that it's bigger.
Yeah, holy shit. Maybe. If somebody told you there's a 1% chance you're going to meet somebody with green eyes, and you turn the corner to somebody with green eyes, you're like, wow, I think you're full of shit, right? That's immediate evidence that they know something just happened that you said there was only a 1% chance of happening. I think your claim is wrong. Does that make sense? Okay. Really, because that's the whole idea. So if we take a sample, not only does it have to be bigger, it's got to be bigger enough. To the point, this is the reasonable doubt thing. 1% is crazy, right? So if we do get something up here, it is more likely that the mean of these coyotes is actually bigger. It kind of means the whole picture should be drawn more up there, maybe. We don't know exactly what the average is, but it's evidence that it's more than 10.15. Does that make any sense? This is really weird shit. But statistics, it's all about the distance. And in this case, it's actually more about the probability. All right. Yes?
I think I just am having trouble remember exactly what alpha is defined as.
Oh, yeah. So the beautiful thing about alpha, looks like a fish. Fish have tails.
Okay.
And alpha is the Greek letter A. So it's the area and the tail or tails. It's kind of crazy. The symbol itself looks like a fish, and it's the Greek letter A. All right, it's the area and the tail or tails. So if there's a two-tail test, it'd be the total area in both tails. Okay. All right, now, part D is also old news, but I use a different symbol here, and this is just me. So let me say this again. I know I'm repeating myself, but it's just the way teaching works. This is what we're talking about. This is what we're allowed to use to talk about it. This is where does evidence start. Now we're going to see, did we find enough evidence? Now we're going to see how far did our sample get. Our sample has to get here, right? In fact, here's what I mean by put it into words. If I calculate a z-score for our sample, when would it be enough evidence to say that this guy's wrong, to say that this guy's right? How far would it have to get?
Unusual, some more than 2 standard deviations.
No. Remember, the whole thing about yesterday was we're defining unusual differently. So before, we just accepted unusual is always 2 steps away. Now, what's unusual? 2.326 steps away. Which, to be honest, is more real life. Unusual shouldn't always be the same. If I'm, again, the nuclear power plant thing, I'm going to get off my ass the minute it starts to move towards the yellow. I'm not going to wait for it. It's not unusual yet, right? Okay.
Wait, what is the current unusual? I'm sorry.
Say again?
The current unusual, what's the new word?
So in the past, it was 2 steps away. Why was it 2 steps away? Does anyone remember why we decided 2 steps away should be what unusual is?
Normally it should be that's like 60%, 66%.
Within 2 steps was what percent? 1 step, 68%. 2 steps, 95%. So what was outside?
2.5%.
So 5% total. So wouldn't we all agree that defining something that has a 5% chance of happening, it makes sense that would be something we would consider unusual? All right. Now we're to the point where we're like, okay, that was nice, but different situations require a different idea of unusual. This sense of unusual is 1% chance, and it leads to it being this far away. This is a z-score, correct? Okay, you're all like, yes. So that's why I gave the symbol. When we calculate the z-score for our sample, when we see how far away our sample got, I'm going to call that z star just to differentiate it. And you'll see another reason why I do this in a bit. If our sample is more up than 2.326 standard deviations, what is that evidence in support of? Which one of these people? If we get way the shit up in here, which one of these does it evidence for? You could do it. Which one of those thinks that it is up? Which one of these statements? Which one of these people? I always think of these as 2 little old men. HA. That's the one that thought it was greater, correct? So if I get in here, I can support this guy. I can reject this guy. So if our sample gets up here, that is so far above what the HO thought, that he must be wrong. Or it's evidence that he's wrong. If that's, then we can reject. You'll left this. Reject the hope. So reject the null hypothesis. Support the alternate hypothesis. Yes.
I just want to make sure I just have this all wrapped up nicely. So now, when unusual stuff is considered unusual based on a problem with alpha given.
Yes.
And that's how we define our new. So in this situation, because alpha is 0.01,
Yes.
z-square is 2.36 or 2.326. Beyond that is unusual.
Is unusual.
Okay. So if a different problem with alpha, that would be 0.2 or 2% chance.
Yeah.
To get that different
Yeah.
z-score, and whatever
Yeah.
that z-score would be our new
Yes.
unusual region. Okay.
So in real life, the alpha depends on who we're trying to prove something to. So again, like I said, if you're trying to prove to your insurance company that your rates are good now, their alpha is going to be like 0.005. It's going to be some stupid hard test to pass, right? Does everybody understand what I just said? 0.01 versus 0.005. Which one would be harder to pass? Because that 0.005 would be even further up. It would be a smaller tail, right? That would make it harder for my sample to get that far away. 11. This is beautiful because alpha, all right, you're going to love this shit, okay. Alpha, when we're talking about hypothesis test, is also called the level of significance. Did I spell that right? Significance. I can't remember how to spell significance. Okay. It's a good thing I teach math. Would it be more significant if I passed the test where alpha was 0.005? Because that upped the stakes. That made it harder for me to get that far. Okay. So let me say this real quick. I kind of like this example. Let's say I'm the coach of a football team. And one thing my football team is missing is somebody who can actually run fast. Most of my guys are big, they can't run very fast. I need somebody who can run fast. You guys with me? Everybody sort of with me? Even if you don't like football, you understand what I'm talking about. Okay. I put out a call and people come in and what am I going to do to see who should join my football team? What do you think I'm going to do?
40-yard dash.
Yeah, some kind of a dash, some kind of a thing. So it depends on, do I want them to be able to be quick or do I want them to be fast over a longer thing? So I set up some 100-yard dash. 100-yard dash, because that's the length of the football team. Are you, everybody with me? So 100-yard dash, everybody who comes, they're each going to run it. How do I determine who should join? Not even necessarily the fastest one, but I'll probably put a benchmark, right? Like I'll say 1% of people can run that in this time. So I'm going to set that to be my benchmark. Anybody who does it faster, I'm going to consider to be on my team. And then I can look at other things, right? Does everybody understand that? So this is a benchmark. I'm saying I am not going to say that the null dude is wrong until I get a sample that meets past this benchmark. Then they could join my team, right? Maybe. Okay. So again, what are we talking about? What are we allowed to use to talk about it? Where does evidence start? Did we find enough evidence? So now we can calculate the z-score. And this is another old one. So see how I say summarize the sample information? Can anybody tell me anything about the sample that was taken in this problem? Anything?
It was 2.35 years higher.
No, just what did they see from the sample? What did they see?
There's an increase in mean lifespan.
No. They didn't see an increase, they saw a certain amount, right? So what was the mean? What was the sample mean? Let's go like that.
12.45.
12.45. Now somebody else tell me anything else about the sample.
41.
N is 41. Somebody else tell me something else about the sample. Do we know anything else about the sample? No. What standard deviation do we know?
4.27 years.
11. Did we take a sample? This is a silly question. Did we take a sample? Did these people take a sample? Yes. Am I talking about sample means? Yes, so what needs to happen? What will always happen here before I calculate a z-score? If I take a sample and I'm talking about sample means, what do I need to change? Standard deviation. So the new standard deviation is going to be the old one divided by square root of 41, square root of n. That will always happen because every time we do a hypothesis test, we're going to take a sample and we're going to be talking about the sample means. Uh, 0.6, I don't know, 0.67, sure. Do it in my head, so I could be very wrong, so don't worry if it's not 0.67.
Yeah, 0.66686.
Dudular. So 667?
Yep.
Okay. Okay, I like it. So that's old news. We've done that shit before, right? And I'm calling it Z star, and the only reason I do that is because there's already a Z score here. So I just wanted to differentiate. This is the one we're calculating, this is the one we're trying to beat, right? To show evidence for HA, we're trying to beat this. So it sees always our data. Our data is 12.45 minus what we're assuming to be the middle, 10.15. So it's always going to be our data minus the number from the claim. We're going to assume the middle is this, and we're trying to find a contradiction. Divided by the new standard deviation. 3/2, 2.3, 1.15, 3.45.
Damn.
Yeah, okay. I just got to flex that because this is my one skill. So. Let me stop for a minute. Let me just stop. I really want. I desperately. I know we get lost in the nuts and bolts. We get lost in this. That's why I try to show you an overarching idea. What are we talking about? What can we use? When does evidence start? How far away is far away enough? Did we get far enough away? Did we get far enough away? Where did we end up? If you put that on the picture, where is that?
3.45.
It's way the shit up here, right? So there's another reason why I call it Z star, so I could put a little star on it. We just did something that would be really unlikely if the mean really is 10.15. So what's more likely is the mean is actually bigger. I really want that. So watch this. Those of you at home, don't worry. Shut up. I don't know if you can even see this. That's great. You can see most of it. Okay. What was I about to do? Damn it. Took too long, Jeff. Okay. So 10.15. If that really is the mean, any sample we take should show up in here. Yes? Should show up kind of close to that. We just did something that is really unlikely, assuming that's the real mean. Therefore, what's more likely is the picture for coyotes that have more room to roam is probably up a bit. How much up? We don't have a clue. This kind of a test cannot show us what the real mean is. It can show evidence that the real mean actually is different. That's all it can do. Which is all we need to know for a lot of things. If we did this study, does that mean that other zoos and other places, other conservancies, should they increase the room that their wolves have to roam? Or the coyotes, I think it was. Yes or no? If this study happened and I have a conservancy or something for coyotes, should I give them more room to roam than the current average or whatever? Yes, the study seems to say. And of course, it kind of makes intuitive sense, but, you know, yes.
Even if it's just the one study?
Well, good point. I would want this to be replicated, but if this was replicated,
Okay.
and it had this kind of coyote, I keep saying wolf, then I should consider increasing the room they have to roam.
Because if it was replicated and they also got that really unusual thing to have multiple.
Yes,
really
then it
unusual
really
things
starts. Exactly.
absurdly,
Yeah.
like,
Now, if somebody did another study and they got a Z star of 2.15, right? That by itself would not have passed this test. Does that make sense? If our Z star was 2.15, we wouldn't have made it in here, would we? So then that would have failed. But combined with our stuff, that's still kind of like evidence in our direction. And then if you do another one and it actually gets in here, now it starts to be like, okay, this seems to be just true. Is everybody sort of with me? I really will. And that's why in science, replicability, being able to replicate something, did I just create a new word? Being able to replicate results is huge because of what you just said, right? Could we have just happened to pick a sample that just happened to live longer? They would have lived longer no matter what. Yeah, that could have happened. That's why it's got to be far enough away. I love it. You're all, I know. You can't even see what I'm doing. Okay. So this is a little weird today because there's concept and there's nuts and bolts both coming at you at the same time. It's kind of the way it has to be though. Okay, so again, these two steps are the most important steps. When does evidence start? How far away do I have to get? Did we get far enough away? Now, what did we say up here we could do if we did get greater than 2.326? We did, right? So what can we do then? We can reject
null hypothesis.
the null, right? And support the huh. So I used, let me see where, but yes, up here. I haven't said this word yet, but now I want it to really, really make sense. Do you see how I call this the rejection region? Why would I call this the rejection region? Because if our sample gets in there, we can reject the null hypothesis. The name rejection region makes sense. I think the book calls it the critical region, which is just dumb, but it's okay. They do what they want to. So again, if there's a claim that the mean is something, well, if I get far enough away from it with a sample, that should be evidence that the mean actually is not that thing. This step just clarifies what far enough away means. In different situations, it could be different. Is it possible that, so what would, let's do this first, I'm sorry. What's our conclusion then? What do you guys, let's just say it like this. Who seems to be right? Which one of these two guys seems to be right?
Okay.
The alternate dude, right? Okay. In fact, which one of these was the claim? The alternate. Okay, so your conclusion always has to talk about your claim. So in which case, I'm not going to use this language because that our claim was not the null. I'm going to use this language. So here we go. Here's how this is going to be. This is going to be a lot like the confidence interval. You got to write a conclusion. We have found sufficient evidence to support the claim that plagiarize that the northern Minnesota coyote lives longer in captivity if they're given more room to roam. Oh my God. That the northern Minnesota coyote lives longer if given more room to roam. Okay, that's all I can say. Okay. Again, you know, generally don't plagiarize, but in this case, the conclusion has got to address the claim directly. So then you can just go write down what the claim was. Okay, you all are an appropriate level of excited about this. This is good. I don't care about excitement. I just care about does it make sense. That's all I want. So one little thing I skipped because it's currently the least important thing, but it's going to become the most important thing. There's one little thing I didn't do yet, and that is this weird ass dude here. P-value. Can you just tell me your gut reaction to 3.45 z-score? Is that close? Is that far? Is that what it's? It's very far. Shit, yeah. The p-value. Okay. All right. I know there's a lot. What was the area in this tail called again? The area in this tail. That's the rejection region. That's what the region's called. What was the area? Alpha. 0.01, right? Alpha. Everybody with me? The area in the tail that this z-score makes is alpha. The p-value is the area in the tail that our z-score made. Didn't our z-score make a tail? It's got a little tiny, look at him, little tiny. Is our tail going to be more or less than 0.01 that our z-star made? There's a little tail that our z-star made, yes? All right, let me put it up here because that picture I've got up there is just sort of getting really inundated. All right. 2.326, there's alpha, yes? And it's 0.01. Our z-star was 3.45. You see that tail here? Is that going to be more or less than 0.01? A lot less, correct? And you guys can right now go find it for me. Look it up. How the shit do you find the area in that tail? This is chapter 6 stuff now, which was ages ago. Not really. I can see your face. You're all like, I'm so happy I came to class today. This is great. Right, if you look up 3.45, you're not going to get the answer, right? Because that's the area below. You want the area above. So what do you get when you look up 3.45?
9.9997.
99997. Okay. So then what's the p-value then? It's going to be the area in this tail. 1 minus this, right?
0.0003.
This, let me say this very carefully. The p-value is related to the probability that we would get a sample where we did, if 10.15 was the real mean. So if 10.15 is the real mean, there is a 0.03% chance that we get a sample where we did. So holy shit! I'm like, that mean ain't 10.15. Now, is there a chance I'm wrong if I say that? Yeah, a 0.03% chance I'm wrong, and that's a hell of a lot better than my normal chance of being wrong. Let that make sense. Okay, I think what I want to do, and some of you guys are like, let us out early? No. I think what I want to do is, before I give you this handout, I'm a little upset at myself that I forgot to change something. We're going to do an example together on the board, and then I'm going to give this handout out, and you're going to try a problem on your own. And by the way, before I forget, the way that Chapter 9 works, 9.5 is the first section where you do an entire hypothesis problem like this. 9.1 deals with this piece. 9.2 deals with another piece. 9.3, it kind of like chunks it up. 9.5 is the first place you see an entire problem that you have to do. You're with me? Also, before I forget, the book says use the worksheet in the back of the book to do these. Screw that. Everybody hear me? These are the 5 steps. These are them. Right? So if I'm you and I'm doing Chapter 9 homework, 9.5, I'm going to have this worksheet sitting next to me. Why do I do that? Because the book, they plug shit in the calculator and just get a bunch of numbers, and then that's what the worksheet's based on, is the numbers you see in the calculator. Okay, I like it. So we don't do things like that. Okay. So let's do this. I'm going to make up, this should be exciting. I'm going to make up one here on the board. Let me let you sleep for a moment. Okay. So let's see. We feel tired. No, we feel that the average final exam grade for Jeff's stats class is at most, I don't know, what do you guys think?
Perfect.
Is it most 100? That's going out on a limb. 78, okay. The average grade is 70, is at most 78. Okay, we take a sample. Of 47 final exam grades over the years, right? And find sample mean of, what do you got, Jeff? You can do it, buddy. You can do it. Of 79.8 with a standard deviation of blah, 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 blah. 10.15. Sure. So this would be 0.2. It's not too terrible, John. Yeah, that's fine. This one. Okay, this will do exactly what I wanted to. The sample mean, doesn't it seem to show evidence that we're wrong? And of course, we don't know yet. So this is a neat one. The claim is not always going to, let me not say that because I want you guys to get this. So step one, what's the claim? In Mathish. So in English, what's the claim? So you always look for words like claim, or feel, or believe, right? That's somebody's claim that they're making. So what's the claim?
It's at most 78.
At most 78. So how would I write that in Mathish? At most 78.
My brain's telling me it's less than,
Good, your brain is right. Less than
less than 78.
or equal to. That's at most 78. So you could be at most 12 to eat off the kids' menu, right? So if you're 14, too bad. If you're 14, damn. Good job taking this college class. All right. Which one is that going to be? The ho or the ha? Which column? Oh.
Oh. Yeah.
Easy when you walk right in, I'm sorry. The mean is less than, yeah, why is it the null hypothesis? Because it has a equal sign, okay. The way we set it up again, the ha will always be the one that tells me how many tails and where they are. What will the ha be here?
Less than.
Opposite of this. Greater than. The opposite of less than or equal to is greater than. And the funny thing is, if you have a symbol, an inequality symbol, the arrows have to be pointing in opposite directions so that they're opposites of each other. So how many tail tests will this be?
1.
Yes. And where will it be?
Left side. No, wait, right side. I'm sorry.
The great thing is, again, the ha sets up the rejection region. The direction the arrow is pointing will tell you where it is. It's crazy. Okay, let me stop for a minute. In this case, if that is how we feel, are we hoping to find evidence? Are we hoping to get a sample in here?
Yes.
Are we? Which one do we feel is true?
Oh.
We feel this. So we're actually hoping we don't get in there. That's freaking science. That's what science is constantly doing. We have a theory. Okay, let's try to disprove that. That's what it's like. Okay, that didn't disprove it yet. That didn't disprove it yet. So the theory of gravity has not been disproven yet. It's been improved upon, but it has not been disproven. Right? So science real quick little thing. Science loves the shit out of when somebody goes, oh, this well-established belief is wrong. Here's evidence. And then scientists are like, whoa, that's exciting. Holy shit. Right? Nowadays, there's a few too many people that feel like that's not true, which really gets me upset because that's the fundamental thing about science is, oh man, if we could show this is wrong, that would be so exciting. Okay. Especially when it comes to vaccines. Okay, we're not going to do it. All right. Whoa, okay. So this is obviously a one-tail test. Okay. Second step. Man, I've given myself no room up here. Okay, I can squeeze it in. Second step. Z or T? This one, I like the way I've worded this one. Did it on purpose. Basically said, I like the problem I just made. Good job, John. What's the two things you have to look for? What's the important thing that tells me I could do something? Is it normal? What tells me if it's normal? Did I say it's normal? Nope. But?
Sample size.
Sample size. Greater than 30. Check. So now I can see Zort, right? Z or T. What do I look at to tell me which one I'm going to use? Standard deviation. T-scores were invented for when I don't know sigma, when I only know S. So be really careful. I didn't say which one it is. I just said there's a standard deviation. Where did that standard deviation we got come from? Where did it come from?
The sample.
The sample. So do I know sigma then?
No.
Oh, the only one I know is this, and that's from a sample. So sigma unknown. So what do we have to use? T. Can we stop for a minute? I'm just going to keep going with different colors. Why not, Jeff? Third step. Rejection region. You're kind of dying, little dude. I'm sorry.
How are you doing?
You're good. Let me say this. I didn't say it yet. Let's use alpha equal to, what do you got, buddy? Point, sure, 0.05, yeah. Hey. So can you figure out what the rejection region Z-score is going to be? So we know it's up here. So one-tail test, 0.05 Z-score, I'm sorry, T-score. What do you need to know to be able to look that T-score up? You have to know the degrees of freedom. So what are the degrees of freedom? I don't even remember if it's on here.
46.
46, okay, 11. This is a perfect. Is 46 on there?
No, sir.
So what do you use?
45.
45, kick ass. So alpha is 0.05, one tail test, right? One tail, so I'm looking at the top row. 0.05, it's right over there. And then stop at 45. What do you guys get?
1.675.
Yeah.
Quick question though.
Yes.
Do you round up or down based on how close it is, or do you always round
Yeah,
up?
based on how close it is. Yeah, yeah. So if it was 49, right?
Right. it'd be-
And you use the one for 50, I'd be okay with that. Technically, you should always go down, but if it gets really close to the next level, you just use that one. Yeah. 1.679, is that what it said?
Yeah.
Okay. So, you ready? Watch this. If T star is what, then we can reject the null, support the hot. Where do I have to be? T star, how far my sample gets, has to be further than 1. It's kind of a silly question, right? We got it up there.
Should I-
How do I get into the rejection region if I'm greater than 1.679? Reject the hoe, support the hop. Okay, I like it. So again, what are we talking about? What can we use to talk about it? Where does evidence start? Like how far away is far away enough? Next step naturally would be how far did we get? Right? Did we get far enough away? So step 4 is what's the sample information? N was
47.
47.
Sample.
X bar is
79.8.
79.8. S,
SE, or like standard deviation, 10.15.
now here's the part where people are gonna freak out, okay? And you're all like, here's the part. What does this symbol mean?
Sigma standard deviation.
Be more specific.
How far-
Beautiful, be more specific.
How far on average it is away from the mean.
Be a little less specific. Alright, alright. What's the difference between these two? They're both population standard deviations.
The standard deviation of just everything in general and the standard deviation of the sample. So the standard deviation of the population and standard deviation of the sample?
Nope. No, definitely not. You're okay, Laura. Thank you. I kept saying this. This was calculated based on individuals. This one it works for groups. Everybody with me, right? Isn't that what I kept saying? This one was based on individuals. This standard deviation here, believe it or not, is based on individuals. Didn't we calculate it based on every individual person's grade? Yes? So it works the same way. This is where people get freaked out. I have S. We know S, yes? That's still for individuals. I need a spread that works for groups of 47. Aren't we working with a group of 47? I still need to figure out the new standard deviation. I still need to do this. No matter which thing I'm talking about, I still need to make it into one that works for groups. The way you said it first, Robert, is the way a lot of people kind of come away with it. That's the population, that's the sample. No, these are both populations. They both have the Greek letter. This is the population of individuals, this is the population of samples. So this one is the standard deviation for individuals, this is the standard deviation for samples. I still need to do that for the exact same reason. Okay, so here, S sub x bar is going to be the old one divided by the square root of 47. Is that the same number I used before? I don't know.
No, the last one was 41.
I'm so different. Okay. Do you have a guess for that, Jeff? I don't know. 10 minus 7 is 1.42. So like
1.4805, or just 1.481.
Let me stop for a minute. We've done this before. Well, not really. We haven't looked at S and changing it, but it's for the exact same reason. You always have to do that because the standard deviation we're given was calculated for individuals. I'm sorry, I'm just laughing. You are reacting the exact same way you should. Okay, I like it. Now, you ready for this? T star. Ah, shit, Jeff, whatever, man. So we're talking about T-scores. The great thing is the formula doesn't change. It's still our data minus the middle divided by the spread. So it's going to be, what was our data? 79.8 minus the supposed middle, 78, divided by the new spread, 1.481. 15, 1.2 something.
1.215.
1.22?
Yeah. I was just keeping in the thing of 3
this in the right direction? No. Did we make it far enough away? Come back to the picture up here. That's why I want you to draw this picture.
No, we didn't.
We didn't. We made it here. That's exactly where the null would expect something to show up. It would expect it to show up in here. So sure, it was greater, but was it greater enough to kind of like beat the fact that there's going to be variability? No. It was kind of like in the range where this statement would expect it to be. Now, so we did not find evidence. Are we sad about that?
No.
No, because that's our claim. We didn't want to disprove it necessarily, right? Now, to be honest, if you think about it, you're like, well, I wish the mean was higher, Jeff. What the hell's wrong with you, man? But too bad. Okay, maybe. So, we did not find enough evidence, correct? We are unable to reject this. Does that mean this statement is true?
No, it's just supported.
If we find somebody guilty, does that mean they actually did it?
No.
No. If we find somebody not guilty, does that mean they're actually innocent?
No.
Which is why we say not guilty. I don't know if you guys are with. So we assume you're innocent, but then if we don't find enough evidence, we say they're not guilty. We don't say they're innocent.
Hypothesis.
Because we haven't found enough evidence yet. Doesn't mean you're not that you're innocent. It doesn't mean you didn't do it. All of that is to say this. We never accept this. Even if we fail to reject it, that doesn't mean that it's true. We just didn't find enough evidence. If we go and take another sample, maybe that one would show enough evidence. Yes? So it's either you reject the null and support the ha, or you fail to reject the null, fail to support the ha. So in this case, we fail to reject the null, and we fail to support the alternate. Egypt. Like half of you can see what I've written. I'm sorry. I really hate this mountain of stuff here. Now everybody's favorite step, step 5. We have to write the conclusion. What time is it? Okay, we'll take a break when we're done with this problem. So the conclusion. Okay. Step 5. Conclusion. So did we find enough evidence or did we fail to find it?
Not find enough.
So we have not found. Oh, by the way, before I forget, which one was the claim?
At most.
No. Which one?
H alpha.
No.
Or at most. I'm sorry. Yeah.
So the whole is a claim. So which language are we going to use? Not this one. We're going to use this one. Fail. We have not found sufficient evidence to reject the claim that plagiarized. So at the end of this, you don't have to guess what language to use. You use the exact language related to which one was the claim. If somebody says, if I'm a consultant, I'm a statistician, somebody says, I have this claim, test it, and I go do it, and I come back, I'm going to have to tell them something about their claim. Was my claim right or was my claim wrong? So when I write the conclusion, it has to be talking about the claim. So we have not found sufficient evidence to reject the claim that the mean was at most
78.
where'd it go? Yeah. The mean grade is at most 78. So depending on, in science you shouldn't go into something hoping it comes out one way or the other, but if that's our claim, we sort of don't want to disprove it necessarily, right? So we're not like, if we fail the test, it doesn't mean we're actually sad necessarily. That's all I'm trying to say. Now, one thing Oh shit, we never did we? Damn it. Real quick, for that problem we did before this, our z-star was 3.45, right? I talked about the p-value and then I never actually got, well, no, we did, didn't we?
Yeah.
0.0003, right? How did you find that?
Z-score.
Z-score chart. Okay, I love it. This one was about t-scores, yes? Does anyone understand that the t-score chart is nowhere near as detailed as the z-score chart? If I wanted it to be, every degree of freedom, I would have to have a z-score chart amount of information for each one. So I'm never going to ask you for the p-value for a t test because you don't have enough information. You could estimate it, but I'm not going to do that to you. There's enough to worry about already. Okay. In that regard, let's take a break. Let's take a freaking break. So, come back, I don't know. 10:40, is that right? Yeah, 10:40.